Hi, today we're going to talk about how magnetism and electricity are related, in particular electromagnetic induction and electromagnets. We use both of these concepts extensively in aviation electrical systems. We'll talk about electromagnets first. So what is magnetism? A magnet is a body that has the property of attracting iron and producing magnetic fields external to itself. The magnetic fields consist of flux lines. They're invisible, but they extend out past the magnet. Everybody, I think, has played with magnets, and so you know that they interact with one another before they touch. Flux lines exit the magnet at the North Pole at right angles to its surface and enter the South Pole at right angles to its surface. Electromagnetism is where we create an electromagnetic field with electricity. And so we are essentially producing an artificial temporary magnet with electricity. Instead of shooting out the ends of the conductor, the flux lines encircle the conductor. The stronger the current in amps, the stronger the flux lines are. So this picture represents a conductor, a wire, going vertically, and the electrons are passing from the bottom of the figure to the top. The flux lines are generated around it, invisible, and they are circling clockwise in this case. If you were to sprinkle some iron filings on that piece of cardboard and then jiggle it around a little bit, the iron filings would align themselves with those circles and you would actually see the flux lines. The flux lines rotate in a specific direction. We use what we call the left-hand rule to figure out which direction they're flowing. Now, this is not something you need to know as a pilot, but it does help you understand how we can apply this theory to create a usable magnet. So if we point the thumb in the direction of the electron flow and wrap our fingers around the conductor, hopefully it's insulated so we don't get shocked, then our fingers point in the direction of the flux flow. We can use that knowledge to build an electromagnet. This figure shows a core, an iron core, that has been wrapped with a conductor. The electrons are flowing from the right hand end of the conductor to the left hand. And as they cross over the top of the conductor, we can see that the magnetic flux lines are circling in a counterclockwise direction. And as they come at us around the back towards us on the bottom of the core, we can see that the flux lines are rotating in a clockwise direction. You can sort of think of those as creating a set of gears that force flux lines through the core and create flux lines in the core as if it were a magnet. Those flux lines will continue to be there as long as we apply electricity to the coil that's wrapped around the core. Probably the most common application of electromagnetism is in relays. Relays are very common in aviation diagrams, and they have other names as well, contactor and solenoid. They take various configurations, but they all mean kind of the same thing. We use a temporary magnet to open or close a switch. In this diagram, if we trace the electricity from the battery and through the coiled wire that's wrapped around that core to a switch, then we can see that if we close the switch, we now have current flowing through the coil, through the master switch to ground, and then from ground it goes back to the battery. So we have a closed circuit there. That electricity flowing through the core causes the core to become an electromagnet, which pulls down on the contact above that is suspended by the spring. Once this is done, it completes the circuit from the battery to the load so that we essentially use a very small switch to open and close a very heavy-duty switch. And that's what relays, contactors, and solenoids do. They allow us to control a much bigger current with a very small switch that can fit nicely into our instrument panel. So, electromagnetism. It is essentially creating magnetism at will. By running electricity through a coil, we can create a magnet. It doesn't take much current to create a small magnet that's capable of throwing a switch. The opposite works too, though, and we call this electromagnetic induction. If we move magnetic flux lines through a conductor like a wire, the electricity will flow through the wire. You can kind of think of it as dragging the electrons through the wire with the magnet. You can actually conduct this experiment yourself. If you have a small, fairly powerful permanent magnet and a little loop of wire attached to a very small light bulb that doesn't take much current to run, you can just whip the magnet back and forth across the wire and you can watch the light flicker. Anytime a conductor passes through flux lines, electrons will move through the conductor. It also works if the conductor remains stationary and the flux lines move. The quicker the movement, the more current is induced. The more powerful the flux lines, the more current is induced. This is how we generate electricity in the aircraft to keep the battery charged and supply enough current for our electrical system. We do that in the form of generators and alternators. Both of those devices use electromagnetic induction. We also use electromagnetic induction in things like transformers to change the voltage in alternating current circuits. It can, however, also be a nuisance in the aircraft. If we have some source of flux, and it doesn't have to be a permanent magnet like shown here, it can be a wire with some real current flowing through it. If that current changes, so let's give the example of the beacon on the aircraft, which is turning on and off constantly. The wire that supplies current to that beacon has enough current to running through it that it can generate a field of electromagnetic flux. If there happens to be a wire that's hooked to your audio system nearby that, you'll pick that up in your headphones as a little bing, bing, bing noise as when you turn on the beacon. It's usually pretty faint, but after a couple of hours of flying, it can be pretty annoying. When those flux lines either build or collapse, a tiny bit of current and voltage is being generated in the line, and then it quits. As the flux builds again, current is induced again, and you get that next ping. We can get around that to some extent by putting shielding around the wire. From time to time, you'll encounter wire that looks like it has a braided metal sheath around it, and that's what that's for, is to shield the wire that's inside from stray electromagnetic fields that might cause interference.